Hello, my name is Brighton, and as part of the 2023 RISC cohort, I worked on pipe traversal using passive joints and wall pressing wheels. The goal of this project was to improve the effectiveness of Carnegie Mellon's pipe repair robot, which is being developed in conjunction with ARPA-E and Autonomic Materials Incorporated. This robot looks to offer a more economical solution for repairing and restoring legacy natural gas pipelines, which are old, mostly cast iron pipes from the mid 1900s that are prone to leaks and failures. Modern repairs are very expensive because they require digging up the pipe to repair it from the outside or stopping gas flow to repair it from the inside. Our robot should be able to enter the pipeline through an above ground airlock and service kilometers of pipe at a time without interrupting the delivery of fuel to customers. The robot itself is modular with one or more body modules that drive the robot and a disc-shaped nozzle at the front of the train with an array of sensors. It will drive forward through the pipe looking for damage, then back out of the pipe, laying down resin wherever it saw that damage. Real-world pipes are not the perfectly straight and smooth approximations used in the lab. They have elbows and junctions, and especially these older legacy pipes have a surface that is very rough and bumpy. In order to get the nozzle around these corners and prevent it from scraping the walls or getting stuck, our robot needs to be flexible. The design goal is to keep the nozzle centered in the pipe while extruding resin and continue to do so when the pipe is rough and has turns and elbows. The design must be able to do this successfully, both forwards and backwards, without vibrating or shaking, to make sure that sensor readings will be accurate and the layer of resin left behind is smooth and consistent. The design we settled on to meet these criteria is a universal joint between the body of the robot and the nozzle, supported all the way around by compliant wheels. In the prototype, the original nozzle from the robot is printed in white PLA, and the added accessories we designed around it are printed in black for easy distinction. Passive joints are the ideal solution for steering a pipe robot when applicable because they don't require any motors or complex control systems to work, making this design much simpler and less expensive to manufacture than a more common active joint system, which would use two or more servos instead of a mechanical system like the universal joint. The wall pressing wheels around the outside of the nozzle help constrain it within the pipe, which allows it to stay centered and prevent it from scraping the pipe walls. The use of rigidly mounted compliant wheels is a novel idea that is far less complex than existing designs, while having the added benefit of suspension because the rubber wheels can conform to the wall of the pipe, expanding into cracks and compressing over bumps. Ideally, the wheels would lead the nozzle and act as a buffer when it encounters a sharp turn like an elbow, but in order to prevent the wheels from leaving tracks in the freshly laid resin, they had to be placed behind where the resin extrudes from. This design is mechanically simple, but is it also effective? Preliminary results are promising, and the design appears that it will at least work in a straight pipe, but a more complete prototype must be made before driving through curved pipes and attempting a full functionality test of the robot. Here you can see one of the issues with our current prototype. Because the off-the-shelf compliant wheels we were going to be able to find don't compress evenly, they settle on a soft spot and slide instead of rolling, which generates a lot of friction, making it difficult for the robot to push and pull the nozzle through the pipe. The first order of business will be to replace the off-the-shelf wheels with custom 3D printed CPU wheels that will likely look something like this. Once the nozzle is successfully rolling instead of sliding through our straight pipe, then tests may resume in more challenging scenarios, and hopefully an evolution of this design will help this amazing robot when it is deployed in the field. I would like to take this opportunity to thank everyone who organized this year's RISC program and made this opportunity possible, including Rachel Burson, Dr. John Dolan, and Maria Ferrato. I would also like to thank Yiju Ju and Lu Li for their help and mentorship throughout the summer, Dr. Howie Chosette and the Biorobotics Lab for sponsoring my stay in Pittsburgh.